Hello, everyone. This is Meraj Rubayat Kamal. I am currently doing my PhD in the University of British Columbia, Okanagan. And I'm going to present on behalf of Dr. H.M. Muntasir Billah, Assistant Professor of Lake Haiti University, and Dr. Shahriar Alam, Professor of the University of British Columbia, Okanagan. Sorry, they could not come to the convention, so I am presenting on their behalf. And the topic, as you can see, is probabilistic seismic risk assessment of concrete bridge piers reinforced with nickel, copper, and iron-based shape memory alloys. So here is the outline of our presentation. You can see it from here. So what is the motivation of our presentation or our research? Here we can see the effect of an earthquake that occurred in 2016 in Japan. And there we can see a bridge collapse. We all know that Japan is prone to earthquake and they are very well prepared for the earthquakes. But in this case, in 2016, this bridge collapsed. In total, 182 number of bridges had different types of collapses, starting from minor cracking to complete collapse. And you can see this is an interesting picture. This earthquake, and this is a series of 3 earthquakes that occurred in Italy in 2017. And here we can see that during the earthquake, there was no collapse of the bridge. And it sustained some minor to moderate damages. But what happened after 3 months, this bridge suddenly collapsed and it instantly killed 2 people on the spot. So we need to make sure about our construction and design of the bridges. So we have to make sure so that the bridges can perform well during an earthquake, even if after an earthquake. Now, our current seismic design philosophy is based on 2 things. One is the failure. So if we see a bridge collapse, then we call it a failure. And if we see that a bridge is not collapsed, it sustained major damages, but it didn't collapse, then we can call it a success. But there are some drawbacks for this philosophy. If we see that there is no collapse, but there are some major or minor damages, we are calling it a success, but it might result in bridge closure, or it will result in obviously extensive repair costs. And we don't have any specific performance criteria for this. So how can we define the structural performances of a structure that is not a consumable product? We can current design philosophy with the current design philosophy, we can only do that after an earthquake, but we need to have some specific and measurable and attainable criteria for evaluating the performance. That's the idea of this research. So our research goal is to evaluate the probabilistic seismic risk of bridge piers, so that we can keep the bridges operational and minimize the repair need, and most importantly, minimize the residual drift, and finally, to reduce the damage, as we can see here. So how did we achieve this goal? We used an innovative or smart material that is the shape memory alloy bars. This has 2 properties. One is the shape memory effect, and the other is the super elasticity. I think we all know about this innovative material. SMA bars, or the shape memory alloy bars, has the unique ability to undergo extensive deformation, and the deformation retreats back to its original position upon the load removal. That's why shape memory alloy bars can be a strong contender to be used as a reinforcement in the bridge piers. Now, shape memory alloys has 2 different states. One is the Martensite state, which is the low temperature, high stress state, and the other state is known as austenite, that is the high temperature, low stress. I'm going to describe these 2 states here. In the first figure, we can see the twinned martensite state when the bar is unstressed. And if we put on some stress, it turns into the step 2, that is detwined martensite, and the shape is deformed. And when the stress is removed, it turns back to detwined martensite and the deformed state. Now, what happens when we heat this specimen? It turns into austenite state, which is the high temperature, low stress state. And when the heat is removed or it is cooled, it goes back to its initial state, that is state number 1, martensite state. So in this figure, we can see that there is no residual, residual deformation. It has turned into its original position. We can see it from here. After loading, it is going to the point B, between martensite state, and when the load is removed, it is coming back to the point C, and after applying the heating, it returns back to its original position in the austenite state, and after cooling, we can see it turns back to position A, which is its original position with no permanent deformation. And here we are explaining the superelasticity effect. It happens without any impact of any temperature. So at first, it is when there is low temperature, it is in the austenite state. And after applying some stress, it is going to the martensite state. And again, it returns back to the austenite state. So there is full recovery of the stress. And we can see there is no permanent deformation again. So why are we using SMA? Here we can see the comparison between the traditional or conventional steel reinforcement and the SMA reinforcement. We all know that steel always has some permanent set after load removal, but from this second figure, we can see that SMA does not have any permanent deformation, so which is very good for the structures. Even it can return back to its original position after applying 8 to 10% of strain. Here we can see the behavior of the two different types of reinforcements, and we can see the reduced refraction. And in this figure, we can see the methodology of our research. So for this research, circular bridge piers were designed, and the SMA bars, as we can see, the SMA bars are provided at the bottom, and the steel reinforcement is provided on the top, and in between couplers are provided. And the specimen was subjected to 30 different ground motions. And instead of using traditional code-specified design level earthquakes, here we use 3 types of earthquakes. The number 1 is the shallow crustal earthquake. The second one is the mega thrust interface earthquake, and the third one is the deep in slab earthquakes. So we didn't go for the code-specified earthquakes, and the bridge is assumed to be located in British Columbia, Canada. And then next, the performance was assessed by performing IDA, that is the incremental dynamic analysis, and we recorded the maximum and residual drift for each of the motions. And here we use 5 different types of SMA bars. I'm going to show the different types of SMA bars in the next slide. And then the fragility curve of this analysis was done using probabilistic seismic design model, as we can see in the left figure. And after that, the hazard curves were drawn to determine the mean annual frequency of exceeding the different damage levels. We used 4 types of damage levels. I'm going to show that in the next slides. So here, as I mentioned before, these are the 5 different types of SMA bars used in this research. 2 were based on nickel, 2 were based on iron, and 1 was based on copper. And here I'm showing the three important properties that define the performance of the SMA. One is Fy, that is the starting stress from austenite to martensite phase. Then we have epsilon S, superelastic plateau strain length. We are highlighting it here because it defines the capacity to capability to restore to the original position. And the third parameter is the modulus of elasticity. Here we can see the breach geometry of the breach pier, the circular breach pier. I have showed it before. In the bottom, we have the plastic hinge regions where we are providing the SMA bars, and on the top, we are providing the steel reinforcement. And on the right figure, we can see a conventional breach pier, and we can see the creation of the plastic hinge in the bottom, which in the conventional breach pier cannot revert back to its original position. So it is prone to collapse. So for the finite element modeling, in the bottom, we are providing zero length rotational spring, as we can see. And in the red portion, we can see the inelastic beam column element of the shape memory alloy RC section. And on the top, we can see the steel RC section. The steel model was adopted from Manigato and Pinto in 1973, and the shape memory alloy model was adopted from Oricchio and Sapko in 1997, and the concrete model was done from Mander et al. 1988. Then the experimental the validation was performed, as we can see on the two figures. There are two, in the left figure, we can see that we applied two different types of drift levels. One is the 1% and the second one is 2%. And the strain was compared between the experimental and predicted value. And we can see the good performance in terms of predicted value if we compare with the experimental value. The same can be seen for the cyclic response graph, which is located on the right side. In this figure, we can see the seismic hazard and ground motions of the three different types of earthquakes. In figure B, we can see the crustal earthquake, and figure C, we can see the deep in slab earthquake, and in figure D, we can see the megathrust interface earthquake. And these three figures are combined in figure A. And the ground motions are selected by developing conditional mean spectrum, CMS, for the three different types of earthquake scenarios, as I have mentioned before. And as I've mentioned before, we use four types of damage states. DS, we are mentioning it as DS. DS1 is cracking, DS2 is yielding, damage state 3 is the initiation of the spalling, and DS4 is the total collapse. Here in this figure, we can see the results of maximum drift fragility curves. From the first figure is for cracking or damage state 1. We can see that all the 5 SMA bars had similar performance in terms of cracking. But when we go to the yielding, we can see that SMA-3 had a very low yielding in terms of yielding, but SMA-5, that is the blue one, had the highest yielding. But when we look at figure 3, that is the spalling, we can see an interesting behavior. The spalling damage state where SMA-3 has the highest probability of damage. In figure B, we can see that SMA-3 had the lowest probability, but in terms of spalling, SMA-3 has the highest probability of damage, and is SMA-5, which had not a good performance in terms of yielding, performed better in terms of spalling. This can be attributed because SMA-3 has the lowest drift limit before entering the spalling damage state. This might be the reason for this. And here I'm showing the damage state, residual drift limit of the damage state on the rightmost column. And these are the graphs of residual drift. but in this graph has some dissimilarities with the maximum drift curve, as we can see from here. In this curve, for all the damage stresses, SMA-3 had the best performance. It showed the lowest probability of exceeding a certain damage state, as we can see from here. And this can be attributed to higher recovery strain of the SMA-3 bar. And from this figure, we can also see that none of the breach piers showed 50% probability of exceeding damage state 2, that is shown in figure 2. And we designed the bridges for damage state 2. So that's why I'm mentioning this here. And we can also see that the breach piers are performing according to the design performance criteria. Here in this side, we are showing the hazard analysis of the breach piers in terms of maximum drift and residual drift. And we can see that annual probability of exceeding different damage stress for the different SMA-RC piers on the right figure. The vertical shaded lines show the 4 types of damage stress and the probability of exceeding this damage stress in terms of residual drifts. And this table summarizes the 2 different types of damage stress. One is damage stress 4, that is collapse. And from the figure, we can see that all the breach piers had very low probability of collapse in terms of damage, with SMA-3 had the lowest probability of 2.84%. And if we look at the damage state 2, for which the breach piers were designed, again, we can see that these had very low probability. Again, SMA-3 performed the best in terms of the damage probability. So to conclude, we can say that the impact of different components on the probabilistic seismic design model and the fragility of the bridges were evaluated in this study, and which can draw the following conclusions. Number 1 is we can say the recovery strength significantly affects the seismic fragility and risk of the SMA-RC breach piers in terms of both residual and maximum drift. And all the SMA-RC breach piers exhibited very low probability of collapse in terms of maximum drift. And if we consider the residual drift, SMA-3 outperformed all the other breach piers at all damage stages. But SMA-5 had the highest probability of exceeding the damage state 4 and also the damage state 2, as we can see from the graphs as I have shown before. So to conclude, we can say that SMA-RC breach piers will have the minimum annual loss and provide a significant financial benefit, we feel, in the long run, because they had very low probability of damage. So this concludes our slide. Thank you, everyone. And I would like to acknowledge NSERC, Natural Science and Engineering Research Council of Canada, for providing the financial support. And if you have any questions, I have shown the email address of Dr. Billa and Dr. Along here. You can pass the questions to them and emails to them. And you can send me the questions. I can note it down and I can pass the questions to them. Thank you.